Assalamualaikum and good day everyone. We are from JCDCS 1435G and today we'll be presenting an analysis of the waiting line and queuing theory at Chagee. Before we start, here's a quick look at our team members. For this project, we chose the Chagee outlet located in Pusat Komersial Sri Utama, Segamat, Johor. Known for its modern tea beverages and inviting atmosphere, this shop sees a steady flow of customers throughout the day starting from 11 am to 11 pm. From order taking to drink preparation, Chagee operates seamlessly with a cashier and 2 baristas in a shift, making it a great example to know if their multi-phase, multi-server queuing system can handle customer demands effectively. Now, let's explore the characteristic of the queuing system at Chagee. Let's start with the arrival characteristic. At Chagee, the size of the calling population is considered unlimited, as customer can visit anytime within operating hours. The arrival pattern is mostly random, but during peak times, the shop will see higher customer traffic. As for the arrival behavior, most customers are willing to wait patiently in line to get their beverages. Next, let's look at the waiting line characteristic. The capacity of the queue at Chagee is limited by the available space inside the shop. As for the queue discipline, Chagee follows a FIFO, which is first in first out system, ensuring that customers are served in the order they arrive, creating a fair and orderly process. Now, let's discuss the basic queuing system configuration at Chagee. The shop operates with a multi-server, multi-phase system where multiple servers or workers handle different phases of the process. One server takes the orders while 2 others prepare the drinks, ensuring a smooth flow and reducing waiting times. In the first phase, there is one worker stationed at the counter to take orders from customers. As customers arrive, they approach the counter one by one to place their orders and make payment. In the second phase, as orders are being taken, other workers focus on preparing the drinks. By organizing the service into multiple phases and assigning tasks to different workers, the system aims to keep the workflow steady and minimize waiting times, contributing to a more efficient service overall. For this model, we assume that customer arrivals are served on a first-in, first-out basis as mentioned before. We also assume there's no bulking or nudging, meaning customers stay in line until their turn. Customer arrivals are independent and occur at constant rate, following a Poisson distribution, which indicates a random but steady flow. Service times are varied and independent with the average service time known and following a negative exponential distribution. Lastly, the average service rate exceeds the average arrival rate, ensuring the shop can efficiently handle customer demand without delays.
This is our full observation table. We observed this system for 1 hour and we managed to obtain the information for 12 customers in that duration. From the full observation table, now we will calculate the lambda and mu for our first phase in the system, which is order. To calculate the average arrival rate lambda, we need to divide the number of customers with the observation time, and we will get 12 number of customers per hour as our lambda. And for the average service rate, which is mu, we need to divide the number of customers with the total service time, and we will get our mu 42.35 customer per hour. After we were done calculating lambda and mu, we just need to enter the value into the QM4 window. This is our waiting line result. Now, we will look at the parameter column. The first one is the average service utilization, which is 0.28. This section represents the proportion of time the server is busy. So we can conclude that the server is busy 28% of the time, meaning it has 72% idle time. The system is lightly loaded, so customers only experience short waiting times. Next is the average number in the queue, which is 0.11. This is the average number of customers waiting in the queue. So with only 0.11 customers on average in the queue, there is rarely more than one person waiting at a time. Next is the average number in the system, which is 0.4. This includes the customer in the queue and the customer that are being served. The next one is the average time in the queue, which is 0.56 minutes. This is the average time a customer spends waiting in the queue before being served. And lastly, the average time in the system, which is 1.98 minutes. This is the average time a customer spends in the system, including waiting in the queue and being served. So, from this observation, we can conclude that this order system is very efficient with only minimal delays. Now, we will look at the table of probabilities. The column K represents the state of the system, specifically the number of entities customer currently in the system. So, when K equals to 0, the probability is 0.72, meaning that there are 72% chance that the system is empty. When K equals to 1, the probability of exactly one customer in the system will be 0.2. And lastly, this is the table of sensitivity to number servers. Average server utilization in this metric represents the proportion of time that each server is busy. For example, with one server, the utilization is 0.28 or 28%. And if we add another server, the utilization will drop to 0.14. Increasing the number of servers decrease the server's utilization, queue length, and waiting time. But I think the system was already efficient with only one server, so there is no need to add another server in the order system.
Here is the output for pickup. Let me explain how we calculate the value of lambda and mu. The average arrival rate, which is lambda, represents the average number of customers arriving per hour. To calculate this, we use the formula number of customers divided by the observation time. In this case, we observe 12 customers at an observation time of 1 hour. So the average arrival rate is 12 customers per hour. Next, the service rate, which is mu. It represents the average number of customers served per hour. We use the formula number of customers divided by the total service time. Here, the total service time is 66 minutes as summarized at the bottom of the table. We convert it to hours by dividing it with 60, and the calculation will be 12 divided by the value of 66 divided 60, which equals to 10.9 customers per hour. There are two servers in the system. The total service rate becomes 2 mu, and this indirectly make the average service rate become 21.8 customers per hour. The total service rate 2 mu is higher than the arrival rate. This indicates that the system has sufficient capacity to handle the incoming customer demand efficiently. Let's look at the output generated by the QM for Windows. But first, you need to key in all of the value that we got from the calculation, which is the average arrival rate, the average service rate, and also the server, which is 2. This is the waiting line result. From this table, we can see that the average server utilization is equal to 0.55. This means, on average, 55% of the time the server is busy. Second, the average number in queue, which is LQ, is equal to 0.48. This indicates there is on average less than one customer waiting in the queue. The third one is the average number in the system. It is equal to 1.58. This shows that the total average number of customer in system is equal to 1.58. The fourth one is the average time in queue. From this, we can know that the customers spend an average of about 2.36 minutes waiting in the queue. And lastly, the average time in system. It shows that the customers spend an average 7.9 minutes in the system. Next, let's take a look at this table, which is the table of probability. For probability number in system is equal to 0, it indicates that there is 29% that the system is empty. With 99% of the system being empty, it shows that the servers are highly efficient. Other than that, there are 22% of having more than 2 people in the system. With only 22% of having more than 2 people in system, it shows that the system can handle peak time efficiently without becoming overwhelmed. And lastly is the sensitivity to number server. From the table, it shows that the increasing number of servers reduces the average server utilization from 0.55 with 2 servers to 0.18 with 6 servers. From this table, it's also shows that the average number in queue and waiting time drastically decrease with more servers. Staying with 2 servers is already good because with 2 servers, average server utilization is 0.55, mean that they're not overworked. Average number in the queue and average time in queue also acceptable. But if there is an additional cost or notice significant queues or performance issues, adding the third server will show the great benefit. It can improve performance and also with only a moderate cost.
In conclusion, there is one number of server during phase order and the average number of customer waiting in queue is 0.11 customer, while the average time customer waiting in the queue before being served is 0.6 minutes. For phase pickup, the average number of customer waiting in queue for two number of server is 0.48 customer, while the average time customer waiting in the queue before being served for two number of server is 2.4 minutes. Overall, if we compare between phase order and phase pickup, phase order has a better waiting time even though only has one server compared to phase pickup that has two server but still take a long time for customer waiting in the queue. So, is the number of servers provided adequate? Yes, because the maximum waiting time in queue is 0.6 minutes for each customer, which it does not take a long time. Are the customers happy with the waiting time? Yes, because the waiting time is still reasonable and customer satisfaction is slightly acceptable. That's all the presentation from us. Thank you.